It's now 2 p.m. Eastern Daylight Time, so we'll go ahead and get started. Welcome, everyone. I'm Melanie Ross, and I'll be the facilitator for this webinar today. Our presenter is Randy Long. Thank you for joining ANAB for our complimentary webinar on ISO IEC 17025-2017 Statements of Conformance. Please note, we are recording this webinar, so it will be available for future viewing. Some logistics before we get started. Due to the attendance today, everyone will remain muted for the duration of the webinar. Please enter your questions into the Q&A box. We have planned time at the end of the webinar to answer any questions that are asked. Randy is a Senior Manager of Accreditation for calibration laboratories and EMC testing laboratories and inspection bodies at ANAB. He is a qualified peer evaluator for ISO IEC 17011 for APAC and IAAC, and has participated in the development of APAC and IAAC guidance documents. He is a current member of APAC Calibration Working Group. Randy is involved in standards development organizations, including committees in ASME, ASTM, C63, NCSL, and SAE, as well as being a member of ASME, ASTM, and IEEE societies. With that, I'm going to turn it over to Randy for him to begin his presentation.
Good afternoon,
Right,
everyone.
You're now the presenter. I'm going on mute.
Thank you, Melanie. Good afternoon, everyone. Thank you for attending this webinar titled Taking Uncertainty into Account. We'll start with a brief history, talk about the problem or some of the problems, look at a case study, and investigate some solutions.
Randy, you're on mute now.
How do I advance, Melanie?
On the left-hand side of the screen, there's a little narrow white strip that has the like 04 and the arrows there. Yeah, it's not very intuitive.
Part of the objectives here, we'll look at the history of the TAR and TUR. We'll discern differences between test uncertainties, scope uncertainties, and measurement uncertainties. Understand a number of scenarios for taking uncertainty into account when making a statement of conformance, and an ability to determine customer needs and agreeable method for taking uncertainty into account. The least favored and perhaps least understood requirement of 17025 involves statements of conformance and how to factor uncertainty and measurement into that decision, or what's called a decision rule these days. In 17025-2005, it was a very vague statement. When statements of conformance are made, the uncertainty measurement shall be taken into account. Again, this was largely misunderstood in the industry as it provided no goal, and ILAC G8 at the time listed a conflicting shared risk approach where uncertainty was not considered in the decision rule. 17025-2017 provides a bit more by requiring that an agreement between the laboratory and customer on a decision rule exist, and that decision rule employed be reported on the certificate or report. Why is the least favorite? Laboratories don't understand uncertainty very well. They lack tools to automate the activity, and of course, customers often don't understand uncertainty themselves. It's been misunderstood because what does take into account or decision rule actually mean? Laboratories' customers insist on statements of conformance, yet do not understand uncertainty. And then they don't understand the decision rules beyond the basic specification limits. A little bit of history. Collective uncertainty, TAR, TUR, mitigating risk, and where we are today. Bill Standard 45662, which was rescinded in 1994, stated in part that the collective uncertainty of the measurement standards shall not exceed 25% of the acceptable tolerance for each characteristic. In most situations, this was a root sum square of the uncertainty contributors associated with a measurement standard. The TAR-TUR, test accuracy ratio and test uncertainty ratio. On one side of this ratio, you've got the collective uncertainty of the measurement standards. And on the other, you only have the tolerance of the unit under test or equipment for calibration. We could call this collective uncertainty to acceptable tolerance ratio, but you can only imagine the military trying to come up with an acronym for that. This was a qualification to reduce uncertainty to an acceptable level for the purposes of making a simple acceptance decision. TAR-TUR again, hyphenating may have reduced the confusion, and that test-accuracy ratio or test-to-accuracy ratio clearly separates the two sides of the equation. Test uncertainty ratio is an incomplete description in itself, in that it omits one side of the equation completely. TUR would be more appropriately described as test uncertainty to specification ratio. Again, the military used to love acronyms, they still do. The whole idea behind this is to mitigate risk. You have to establish a process robust enough for the equipment to be serviced in order to avoid falsely accepting a device which does not meet specifications. Keep in mind that MIL Standard 45662 was a DoD document for the armed forces with the goal of reducing risk to equipment, personnel, and mission associated with inadequate measurement processes. NCSL International had a guidance document for the Z540-1, which introduced the concept of TAR, or test accuracy ratio, which took that same MIL standard concept of reducing the uncertainty to 25% of the tolerance, and hence was born the 4-to-1 uncertainty ratio, or accuracy ratio, as it were. In the Z540.3 document, which came out in 2006, introduced a concept called probability of false acceptance. They were trying to reduce it to less than 2%, while still allowing for the 4-to-1 simple acceptance. The Z540.3 guidance document working group introduced 6 different methods for determining false acceptance, false rejection criteria, and ways to guard band either measurement results or tolerance limits by that uncertainty of measurement. There's actually several more methods out there now about. A simple acceptance qualified by a threshold uncertainty remains one of the easiest decision rules to employ and to explain to your customers. In ASME B89-731, this is referred to as a simple acceptance with an N-to-1 uncertainty ratio. The simple acceptance with a 4-to-1 ratio is ASME B89's default decision rule for its standards, and it discusses a few situations where that's not the case, but in general, it's 4-to-1. If any of you do mass calibrations, you'll understand that OML, NIST, and ASTM have a 3-to-1 uncertainty ratio for mass calibrations, and that's been the norm for many years. Some accreditation bodies, especially overseas, do not accept what I call an unqualified simple acceptance as a decision rule, since the uncertainty is not accounted for at all. The old ILAC G8 shared risk idea, where it doesn't limit the uncertainty of the measurement. So the problem, what does the laboratory deem appropriate, and does that meet their customers' needs? Since an appropriate decision rule is not defined in 17025, methods often do, but where they do not, the laboratory must come up with something that they can at least present to their customers. So here's the problem. We have a measurement. We have, let's say, a nominal value here. We have a lower limit and upper limit. And here's 2 different measurements with 2 different uncertainties you can see in this picture here. You're still wondering where how are we going to deal with this amount of risk, let's say with a larger uncertainty? You know, two labs making the same measurement may get very similar results, but if their uncertainties are vastly different, then calling it pass or fail becomes an issue. Problem with an unqualified simple acceptance. The uncertainty is not compared to the tolerance limits, and the risk to accepting something that's actually bad is actually pretty high. If the uncertainty is compared to a tolerance limit, and that uncertainty is less than 25% of the tolerance, you can see that even if we're close to the upper limit in this case, the risk is actually fairly low. I mentioned guard bands before. So what in this case, the guard band is modifying the tolerance limit to create a tighter acceptance limit. As long as the data falls between the acceptance limits, that would be called a pass. If it were in this area here, in the guard band itself, some labs might call that a conditional pass or a conditional fail. And same with a tolerance band or an uncertainty band outside. It might be instead of a pass fail, it's a non-binary rule where there's this intermediate area to where it may or may not be accepted or rejected. Here's a slightly different picture, and this is actually from the ILAC G8, where you see you got the measurement uncertainty here around the test value or calibration value. And in this case, they have a binary decision rule where the data, as long as it's within the specification limits, is a pass. But if it's out, even if the uncertainty brings it in, would still be a fail here. Here's a not binary statement with a guard band. So then the rejection here, it's still within these tolerance limits, but it's outside of the acceptance limit. As I mentioned before, some decision rules are non-binary. So if it's within this uncertainty band near the tolerance limit, they might call it a conditional pass. And again, if they took the same guard band and put it outside the limit, they might call it a conditional fail, like you see here. So here you can see the yellow is the guard band or W guard band. So if you've got a very small uncertainty, that guard band is actually pretty small. But if you have a large uncertainty, the acceptance limit can be pretty much to where you don't have an acceptance limit because there's no possibility of pass if this were your nominal line here. So getting into the definitions of the different types of uncertainties. A CMC on a scope of calibration, the CMC is actually all four of these components here. The equipment that's going to be tested, the range, the uncertainty, and the reference standard or method. So we call this value here the scope uncertainty. A measurement uncertainty is quite simply the uncertainty of a particular measurement. A test uncertainty is the uncertainty of a test, or for calibration-minded people, the uncertainty of a calibration process. The CMC, as I mentioned, is a number of components, including the scope uncertainty. It represents the best case a laboratory can do for their customer. In years past, we calculated a test uncertainty and compared it to a specification in order to determine if we had a process capable of the desired measurement. The military defined as the maximum collective uncertainty 25% of the specification limit. Many laboratories back in the day sought to achieve uncertainties of less than 10% of the specification for routine work while allowing up to 25%. And I think this was largely due to gauge maker tolerance in the dimensional world, where they try to select a tool that's at least 10 times better than what they're measuring. So these were expressed as test accuracy ratios of 10-to-1 and 4-to-1 respectively. And then no work was performed if at least a 4-to-1 was not achieved, as at that point they determined the process wasn't adequate for the desired measurement. As mentioned before, MIL Standard 45662 was rescinded in 1994. Z540-1 was issued. Many United States folks gravitated to the new standard, seeing the perceived weaknesses in the ISO Guide 25, as it largely addressed the things in MIL Standard 45662 that were not in Guide 25. The popularity of laboratory accreditation to ISO Guide 25 in the late 90s in response to QS 9000 Revision 3 began many discussions on uncertainty measurement, and confusion abound. As this happened, many laboratories drifted away from the MIL standard and focused on Guide 25, where there are no specific criteria to determine process capability other than customer needs, and industry trends toward downsizing and outsourcing moved calibration to commercial laboratories and purchasing responsibilities away from technical and engineering personnel. This resulted in personnel requesting services they did not understand, and laboratories were in many cases unable to reach the technical personnel necessary to provide needed information. In other cases, laboratories were reporting that all TURs are at least 4-to-1 unless otherwise noted, yet often no TURs were actually calculated. Where laboratories had test uncertainty ratios, they were not part of any decision rule to either qualify the measurement process prior to the measurement or affect the statement of conformance afterward. A worst case scenario I've described on many occasions is certainly possible. Let's say a customer sends a gauge block, which is a dimensional artifact, into a laboratory requesting calibration, and the laboratory, with contract review language, says that all uncertainties are not taken into account, but then calibrate those gauge blocks with a wooden ruler, stating that the gauge blocks are in tolerance in reference to an established consensus standard, which would be an absolute disaster because a wooden ruler is all over the place. So for a case study, let's say I need to measure a temperature to within 5 degrees Celsius, and I select a thermometer advertised to be accurate to 0.5 degrees Celsius based on the importance of that temperature measurement. I need to have this thermometer calibrated and determined that it's fit for my use. If I send it to an accredited laboratory, I have an expectation that I'll receive an appropriate calibration. If I send this to an accredited laboratory with instructions to calibrate, I may receive a calibration which does not meet my needs, since I didn't define what those needs were. This does not excuse the laboratory from their responsibility, but I would bear some of the responsibility myself. I may receive a non-accredited calibration if that laboratory offers that as a less expensive service. If I send this to an accredited laboratory with instructions for accredited calibration, I should receive an accredited calibration with data and uncertainties. I may receive a certificate which states pass or fail. If I turn around and send this to what I would call a stellar laboratory with instructions for an accredited calibration from 0 to 150C to an accuracy of 0.5C, an example of communication from the laboratory might state, we can perform a 3-point calibration by comparison of your system using a process based on ASTM E2593. Our measurement capability for this process is 15 millidegrees C, and based on your system resolution of 0.01, the expanded uncertainty of your calibration should be 0.06 degrees C. We will guard band measurement results by the measurement uncertainty, changing the acceptance criteria to plus or minus 0.4 to reduce the probability of false acceptance. And I bet no one's ever seen a communication like that. If I send to a Stellar Laboratories instructions for an accredited calibration from 0 to 150 at 0.75 and 150 to an accuracy of 0.5, and it's measurement uncertainty of less than 0.125 and a test accuracy ratio greater than 4 to 1, the example communication from the laboratory might state that we can perform a 3-point calibration by comparison of your system using a process based on the same ASTM. Our measurement process is 15 millidegrees C. What's your system resolution? The expanded uncertainty will be 0.06. We will not guard band measurement results by the measurement uncertainty, as our uncertainty exceeds your requirements with a test accuracy ratio of approximately 33 to 1. In this case, the customer has defined the requirements, which the lab probably loves. Options. A calibration laboratory can ask a client for acceptance tolerance and maximum acceptable uncertainty to establish a test accuracy ratio. The laboratory could inform client of internal requirements for process acceptability and seek the customer's approval. A calibration laboratory could ask a client to define a decision rule for statements of conformance, for instance, guard banding, minimum TAR, acceptance tolerance based on previous reliability data, etc. To propose with a complete description your default decision rule and seek approval for that. And then you should also warn your clients regarding departures from acceptable TARs, TURs, or decision rules. So here I have a sample test uncertainty. And since everybody understands temperature fairly well, because we've all had our temperature taken at one point in time, I use it for this. So in this case, I've got a reference thermometer. I'm using its long-term stability, its resolution, and the inherited uncertainty from its calibrations. I'm going to put this in a temperature bath, and it has a uniformity and stability. And then an overall uncertainty of this test is 0.0097 degrees C. So let's say the same laboratory, for their scope of accreditation, bring in the best unit under test resolution that they want under scope of accreditation, and then they do a process repeatability at what the most difficult temperature for this particular bath is. Now we have an uncertainty for the laboratory for their scope of accreditation of 0.02 degrees C. So if I take this same uncertainty and I replace the resolution with a thermocouple type thermometer device, you can see that the uncertainty best case scenario is going to go up to 0.06 degrees C. So if we look at test accuracy ratios, considering a test uncertainty of 0.0097, let's say we have a typical thermocouple thermometer and its accuracy is plus or minus 2. We have a test uncertainty ratio over 206 to 1. If I look at a different type of device, let's say a thermistor thermometer with an accuracy specification 0.05, you can see that we have a test uncertainty ratio of 5.16 to 1. Now, if I take a typical higher end type sensor like an RTD or a PRT with, let's say, an accuracy of 0.01, you can see that we've got about a 1-to-1 test uncertainty ratio. So some solutions for the users of calibration services. It's best to identify your measurement needs. Search for laboratories with the capability to perform the needed measurements. Communicate with those laboratories to confirm they can meet your requirements for your specific device. Request the specific measurements needed and any pass-fail criteria. And then provide necessary oversight to ensure that your buyer understands and properly executes your request. Once it's done, you review the received service to ensure it complies with your stated requirements. Then you review your data provided to ensure the device meets your measurement requirements. Only then can you actually place that device into active use. Some solutions for the providers of calibration services. One, you should define your own criteria for acceptable measurement practices. Define your criteria for making pass-fail judgments. Advertise that capability clearly. And just keep in mind, if you're accredited, you do have some input into your scope of accreditation. You should define how you select appropriate methods or identify sources of methods and procedures. Consensus standards from standards developers like ASME, ASTM, JIS, etc. are always good. Procedures from manufacturers' manuals are good. And then if you have certain contracts, the GUIDEP or military procedures are actually very well written as well. Prior to accepting a contract or work, clearly communicate your measurement process, your method, not necessarily your individual procedure. Prior to accepting work, question your customers as to what their measurement needs are. Also clearly communicate your acceptable measurement practices. Clearly communicate your default pass-fail criteria. And again, prior to accepting work, discuss any options for pass-fail criteria to meet your customers' needs. And you're also going to ensure that you have the capability to perform the requested service in accordance with your predefined acceptable measurement practices. Then you can accept the work and execute the requested service, verifying that it does meet your customer's requirements. So one thing we want to do is we want to get back to asking for exactly what we need. If you're asking for a calibration service, you don't want to pay for that twice. And you want to get back to the basics of good calibration practices. And I always like to say, you never get lost on the high road. And that happy customers do return. So we've talked about the history of the TAR and TUR. We've talked about differences between test uncertainties, CMC scope uncertainties, and measurement uncertainties. We looked at a number of scenarios for taking uncertainty into account. And we also talked about determining customer needs and coming to an agreement on how to take uncertainty into account. There's a number of references at the back here. ANAB has a good guidance document on reporting uncertainty and measurement. Got the old mill standard here, 17025, and a paper I did several years ago. Melanie?
Thanks, Randy. That was a really great presentation. We do have a few questions that have come in, but I'm going to go over some additional resources to allow the participants or attendees to enter any other questions that they may have into the Q&A tab. A couple questions that did come in is about the presentation. We are recording it, and the recording will be available on our website probably beginning of next week. It just takes WebEx a little time for it to process. So I just want to go over some additional resources that ANAB has available for accredited laboratories or laboratories seeking accreditation. On our website, we have webcasts that are free, pre-recorded videos providing additional information on accreditation and standard requirements. We also offer these webinars monthly. We really appreciate Randy providing the information on statements of conformance. But we offer a variety of different webinars, and all of those are recorded and on our website as well, so you can view those at any time. Our blog page has a wealth of information related to risk, accreditations and standard requirements, and many other topics. And then we also offer training. We offer live online and in-person training, as well as self-paced training in many areas, including internal auditing, standard requirements, measurement confidence, and risk analysis. So with that, we have about 30 minutes left. So I think we'll have plenty of time for the questions that have come in. So I'll just get started. Let me pull this up. So Randy, the first question says, In Mexico, firearms laboratories need to classify a firearm according to some characteristics stated in the law. Does the statement of conformity apply for items that are not measured? For example, a fire selector of a firearm.
I might default this question to one of our forensics experts, but at first glance, I would say no, because it's not a measurement.
Okay, I'll take note of that question and get back to the individual that asked it after speaking with the forensics department.
Excellent.
The next question is, may I know if there are any references for acceptance limits of weights?
The standards that I'm familiar with for mass calibration are ASTM E617. I forget the OIML number, and NIST SOPs. And each of those, the acceptance limits is a simple acceptance based on a 3-to-1 uncertainty ratio. So the uncertainty of the calibration must be less than 1/3 of the tolerance of that particular mass.
Okay. The next question is, may I know if there are any references for acceptance limits of weights in analytical balances? Example, 10% acceptance limits for 0.01 milligram standard weight.
Is this a question about the acceptance limits on balances or masses?
It says of weights in analytical balances. So I think they're talking about the masses there.
In that case, it's the 3-to-1 uncertainty ratio.
Okay. Thank you. And then in drug identification, if you are stating a particular drug is a specific schedule based on a law, is that considered a statement of conformity?
I don't believe so. Again, I would have to defer to our forensics folks.
Okay. All right. Well, do we have any other questions? Oh, here's one. Sorry, this one came in the comments instead of the Q&A. How is a laboratory supposed to handle if the pass-fail criteria is changed after the measurement is made?
That's an interesting question. I don't know why it might change other than the customer changing the contract language or trying to change the agreement. That would have to fall into your contract review process to determine how you're going to handle that. One can imagine that a customer has one tolerance when they send the item in, you measure it, and then they come back and go, no, we've changed our tolerance, and you might actually find that your laboratory is not good enough for this reduced tolerance, let's say. You know, changing the tolerance would change potentially the decision rule as well, or certainly the results of the decision rule.
All right, one more question just came in. Any standard reference / value for measurement uncertainty of sample preparation in food samples testing?
Can you say that again?
I'll elaborate on it. Is there any standard reference or value for measurement uncertainty of sample preparation in food samples, food sample testing?
I don't know specifically if the food testing regulations may have something like that.
Yeah, that's what I was going to say. Typically for food testing, you're using a standard method, and that method will designate, if you follow the method, what the uncertainty is for that method. All right, well, I don't see any other questions come in. I did see a private question come in from a person, but we're not going to address that here. I'll address that separately. I did see that come in. So I just want to leave you all with some additional contact information. If you'd like additional information related to training, you can contact training@anab.org. And for additional information related to accreditation services, you can contact ANAB@anab.org. And if you'd like to discuss our accreditation services or get a quote for those services, you can contact Roger Muse at rmuse@anab.org. I want to thank you all for participating today. And I want to thank Randy for being our presenter. It was a very interesting topic. Everyone have a great rest of your day.
Thank you, everyone.